This is actually probably the closest thing to real engineering that we're going to do in physics class. Right? Engineers that are building roads actually have to know this stuff. I have a friend who's a civil engineer. He sent me a document. It's like about 40 pages thick that explains all this, and I'm like, man, that doesn't make any sense to me at all. All this coefficients and mumbo jumbo stuff. So I put together, I found this on the internet, and I sort of made it my own a little bit. It sort of explains it. But really, motion on a curve is completely dependent upon uniform circular motion.
I don't know if I want to learn this.
The net force on a car traveling around a curve is the centripetal force, Fc equals mv squared over r, directed toward the center of the curve. For a level curve, the centripetal force will be supplied by the friction force between the tires of the roadway. That's important. That one's important, right? If the curve is level, then friction has to supply the centripetal force. As you go around the curve, friction has to hold you on the road and push you towards the center. However,
so is that why we get pushed out because the cars came pulled in? Is that what that force is?
it's because of inertia, right? You're going out.
That car's
Yeah. Now, quite often, if you look at highway curves, you'll notice that they are banked. A banked curve can supply the centripetal force by the normal force and the weight without relying on friction. So the reason for them to bank the curves is to increase safety. You can take the curve at a faster rate, even though friction might be reduced, say, in the wintertime. Okay, so those two concepts are pretty important. So we're going to start with talking about level curves. So here's the top view of a car going around a corner, right? The green indicates the velocity forward, and we have a centripetal force caused by friction forcing it towards the center. Here's the view sort of looking at the rear of the car. You have a normal force up, you have the weight force mg down. For a level curve, the centripetal force will be supplied by the friction force between the tires and the roadway. Here's an example. What must be the coefficient of friction between the tires and the level roadway to allow a car to make a curve of radius 350 meters and a speed of 80 kilometers an hour? For a level curve, the force of friction is the only horizontal force on a car and provides the centripetal force. This can be seen from the free body diagram. So it is friction that supplies that force. And we're going to use mu equals Ff over Fn. So the question here is, it's 350 meters is the radius, and the speed is 80 kilometers an hour.
So for a bank curve, do we start using angles?
We're going to get to the bank curves in a minute. Hang on. So I take my velocity of 80. I divide by 3.6 to get my 22.2. Okay? I plug that into mv squared over r. So it's going to be 22.2 squared divided by the radius 350. You unfortunately don't know the mass of the car. Right? The net force must be horizontal, pointing towards the center of the circle. Only the friction force available to provide it. The normal force and the weight force simply cancel each other out. Calculations are easier if expressed in meters per second, so there's the conversion, 22.2, and we get Fc equals m times 22.2 squared divided by 350, or 1.41 m. The centripetal force is 1.41 m, where m stands for the mass of the car. We got a problem here. Normal force is mass times gravity. We don't know the mass of the car, so the normal force is 9.8 m. Do you get the feeling that the m is going to cancel somewhere down the road? We hope so. For this flat curve, the centripetal force is supplied by the friction force, which is Ff. You might remember mu equals Ff. No, don't do that. Ff over Fn.
Way to go, Mr.
Yeah, I screwed that up. And then it just disappeared.
Like that.
Where'd it go? It's down around.
I'm tired.
You went for a long
Yeah.
walk,
I had a 2-hour walk.
That was silly. Okay, Ff over Fn. If you rearrange that, you're going to get Ff equals mu Fn. Or Ff is equal to mu times 9.8 times m, which is because of Fn here, right? Equal to 9.8 times m. So all I've done is taken this, plugged it in there, right? My Ff is equal to my centripetal force, which I've calculated to be 1.41 m. So mu times 9.8 times m is equal to 1.41 m. And as we expect, our m's cancel. And you rearrange it, you get a mu value of 0.141. So Alex, what does that mean? If you get a mu value of 0.141, it means that the car will go around the corner if the coefficient of friction is less than 0.141?
Or greater than or equal to. I mean, like, you can't be lower.
You can't be lower. The coefficient of friction must be greater than 0.141. If it's just equal to that, it'll just go around, right? Any coefficient of friction greater than 0.141 will keep the car from slipping. This is the minimum value for mu. Notice that the force of friction is perpendicular to the velocity, but it is still in the direction necessary to oppose the motions that would occur without friction. The car will slide away from the center to the right in this diagram if it encounters a patch of low friction surface like ice or oil. Therefore, the friction force is directed towards the center. Notice too that we're dealing with static friction. The piece of tire in contact with the road is momentarily at rest with respect to the road. Even though the tire is rolling, that sort of tire is sort of at rest on sort of a sideways kind of concept. The force of static friction is somewhat greater than the force provided by the kinetic friction if the tires start to skid. So they would actually know what the coefficient of friction, remember what the coefficient of friction was for the rubber tires on the road? It was like about 0.665 or something like that, wasn't it?
0.65.
Something like that. So that means that you could easily take this corner, right? Easily.
Well, I mean, it's 350 meter radius.
350 meter radius is a pretty big corner, right? If it's much shorter, then that's going to increase that coefficient of friction, the necessary one. Okay. Here's where, if you haven't been paying attention, you'll want to, because now we're going to talk about bank curves. And you can take that to the bank, Mike.
Oh.
Civil engineers generally bank curves on roads in such a...
Where is this?
You know what? Okay, so here's my car going around the curve. I'm looking at the rear end of it as it's going around the curve. I need a centripetal force. What's going to provide that centripetal force? Friction. Okay? Keeping in mind that Fc is equal to mv squared over r, and friction force is going to equal mu Fn. Right? Alex, watch. So I've got mv squared over r is equal to mu Fn. 1500 v squared, my radius is, 100. My mu value is 0.65, and Fn is equal to mass times gravity, or I guess in this case here, because I know the mass,
Starting 14,007.
1500 times 9.8.
Wait, is that FF equals M or mu Fn? Does that work for all, or is this only in the circle quite like?
No, he just rearranged the formula.
Mu equals ff over Fn, or ff is equal to mu Fn. Right? Now, some of you might realize that those 1500s are just going to cancel on both sides, right? Hopefully. So you get v is equal to the square root of 100 times 0.65 times 9.8. And you should get a velocity of, anyone get 25.2 meters per second? And if you take that times by 3.6, you're going to get 90.9 kilometers per hour. Now, have you ever seen a road where there's actually a warning, a sign that says you should only take the corner at, say, 90? Right? Why do they do that? Because it's a sharp corner, and they know the coefficient of friction, and they figured this out, and that you should slow down. Do you think that they would put a sign for 90 if they figured out 90.9?
No.
I'm guessing that they probably...
Just probably if it's like 100 or 110.
110, right? Yeah, they've built in some leeway, right? Obviously. But again, this is only true for non-banked roads. This is level surface roads. Mike, you need to pay attention to me.
No, I thought there, figure out the number.
Okay?
What is the 15W there in cross now?
1500 is the mass.
Oh,
In other words, does the mass of the car matter? No. That's a good thing, right? Because cars have different masses. Just because you've got a heavier car doesn't mean you should be able to go faster or slower around the corner. Right? All good? Okay. Let's talk now about bank curves. Now, bank curves are a little bit more confusing.
What about a race car?
What about a race car?
Race car?
Yeah, well, that's the bank curve one. We'll do it. We're going to do the example, and then you're going to try that one. So, go back to this one here. Yeah, it needs to be reorganized a bit. Civil engineers generally bank curves on roads in such a manner that a car going around the curve at the recommended speed does not have to rely on friction between its tires and the road surface in order to round the curve. In fact, if you look at race tracks, they always bank the corners so that they can go faster. Suppose that the radius of curvature of a given curve is 60 meters and the recommended speed is 40 kilometers an hour. At what angle should the curve be banked? Okay, there's a diagram over on the right here. I would like you to write in here, I'd like you to put right here FW. Okay? The triangle that this represents is this one right there in red. It's going to close on me, isn't it? Okay, so that triangle there is equal to this one. This MG right here, we're talking about, is this one here. This F cos theta, this is right here. This is F cos theta. And this one here is F sine theta. All right. Consider a car of mass m going around a curve. The car's weight mg acts vertically downward. The road surface exerts an upward normal force F on the car. This is the normal force. The normal force is always perpendicular to the road surface. So you'll notice here that the normal force is not equivalent to the weight force. That's only true if it's level surface. The vertical component of the reaction must balance the downward weight of the car. So this F cos theta right here has to equal mg. How did I get F cos theta for this component right here? Like if I label this F vertical, right? And this here is theta, right? Then I'm going to have adjacent, hypotenuse, and my theta. Cos theta equals adjacent, FV over Fn, or FV is equal to Fn cos theta. That's where it came from. And the same thing is where this F sine theta came from here. So my F cos theta is equal to my mg. The horizontal component of the reaction, F sine theta, this one here, acts toward the center of curvature, right? This is actually the force. This F sine theta is the force that makes it go around the corner. That is equal to my FC. So F sine theta is equal to my mv squared over my r. F sine theta is equal to mv squared over r. On a banked curve. On a banked curve, F sine theta is equal to mv squared over r. Now, do banked curves matter with mass? Let's hope not.
Oh, wait.
Okay, now here's where you have to fill in some stuff right here, right?
You said you're not supposed to rely on us.
I know, so we're gonna watch here, right? You're gonna see mass disappear. If I take tan theta, I'm looking at this diagram right here. If I take tan theta, I'd like you to write in this spot right here. Tan theta is equal to opposite over adjacent, or F sine theta over F cos theta. Those of you from pre-calc might know that tan theta is equal to sine theta over cos theta.
Yes.
It's probably one of your favorite things. Yeah. F sine theta then is equal to F cos theta tan theta. But what did we say F cos theta was equal to? No, right here, F cos theta. mg. And what did we say F sine theta was equal to? mv squared over r.
Was it F sine?
F sine theta is equal to F cos theta tan theta. I've said f sine theta is equal to mv squared over r, so I'm going to write that right here. And I know that f cos theta is equal to mg. Mass cancels. And then I'm going to write the whole thing as tan theta. I'm going to take the g to the other side over here, and I'm going to have v squared over rt. This is the important formula. On a bank curve, the tangent of the angle must equal v squared over rg. Now, this is only true if you're going at the correct speed. If the car attempts to round the curve at the wrong speed, then mv squared over r is not equal to mg tan theta. However, if you're going fast enough, it's fine, right? If you're not going fast enough, the difference has to be made up by sideways friction force. So this is only relying on the banked curve. In other words, you could use this formula. If you could make a frictionless road, you could actually go around the curve as long as you've worked out all the pieces, right?
So
If you go too fast, then you have to also have some friction involved. Is it possible to go around a bank curve too fast? Of course it is, right? It just means that you've not only gone too fast for this to be true, you've also gone too fast for the friction to be true as well. Right? Added on to that. Okay? And again, civil engineers, they build the roads, they know the curvature, they know the frictional coefficient, they know that people are going to want to go 110 kilometers an hour, so they have to, what's the one thing that the road guy can sort of, there's two things. What are the two things that the road guy can do to make it safe?
make it more of an angle.
More of a bank, and also lengthen the radius. Now, at some point, making the bank, like, you don't want to be going around a corner of 80 degrees, do you?
I do.
Be fun.
Like NASCAR.
But now you got to worry about not going too slow. You got to worry about going fast enough that you don't slide down the road. So they can only bank at a certain amount, right? So the only real thing they can play with is the radius. Yeah. Okay, go ahead and try question 2 there. Example 9, sorry. Example 9, bank curves. Well, what's the formula that I just gave you? Tan theta is equal to v squared over rg. That's the formula I gave you. What's the question? A race car travels along a bank curve at a speed of 120. It doesn't depend on the force of friction to keep it on the track. If the turn is not banked at an angle of 25 degrees to the horizontal, what is the radius of rotation? So, well, the first step, 120 divided by 3.6. Can someone help me out with that? I don't have mine. What is it? What does it? Oh, it does say that there, right? Okay, so you're going to have the tan of 25 degrees is equal to 33.3 squared over r times 9.8, right?
And then multiply on both sides.
The r goes up there, you got 33.3 squared all over 9.8 tan 25, and you should get,
242.
yep, 243 meters.
Hey, got it.
Pretty easy.
Oh, you see 26. Yeah.
Are there problems in that package that I gave you today at the end? And I think they're listed as banked or unbanked and banked, are they not? Yeah. The real problem comes into play when you want to add friction and the banked corners. That gets crazy. Don't worry about those ones. Okay? No. I'm away tomorrow. I'm at a meeting in Brandon, but you've got lots of different problems that you can work on. You can help each other. We are pretty much at the end of UCM. So, how does Monday sound for a test?
What about adding radius bank
No.
curve? Plus it.
I have, exam
Yeah?
all morning.
What day is Monday?